Hello everyone, welcome to the live session for the course Sensors and Actuators. So this is week 6. So if you are watching on YouTube, then I will start the session after few minutes because this is a live session and in last few sessions people have joined. So I'm waiting for a couple of minutes so that people can join. Otherwise I will start after few minutes. Hi Ujjwal. I will start the session after few minutes. I'm just waiting for a couple of minutes so that people can join. You can stay in the meet and I will start after 2-3 minutes. I hope that you can hear me. Okay, and if you cannot you can unmute yourself if you have any question or doubt. If not, then if you cannot unmute yourself at this point, then you can write in the chat box also if you have any query, and also let me know if you have attended the previous live sessions or is this your first live session.
This is my first live session, ma'am.
Okay. So you can access the materials that I have used, like I used earlier in the earlier live sessions. uh, the links you will find in the NPTEL portal for sensors and actuators. There will be one heading like problem solving session. You can find the materials there if you want to access the material for like the last live sessions, last 5 live sessions.
Okay, ma'am.
Okay, I think we can start. It's already 6:05. So first of all, let me introduce myself first. I always start the session by introducing myself. So I am Ananya. I I am a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. My specialization is microelectronics and PLSI, and I'm working here in the Semiconductor Devices Lab group. So we fabricate and characterize many semiconductor devices. Also, we do little bit of simulation, not much. So in our lab, we mostly work on fabrication, and the topics those were covered in this week, like in this lectures videos, like photolithography and all the deposition techniques. Those techniques we use regularly in our lab, although I'm not working in sensors right now. So I did worked on sensors earlier when I was in MTech. So I worked on gas sensors for sulfur dioxide sensing. That was my MTech thesis, and so I will be your TA for the session. So this is week 6. So I'm a bit sick today, so please bear with me. I may not be able to like speak very clearly. If you can't hear me or if there is any problem, you can let me know. Okay. So I always start the session by giving an overview of the topics those are covered in this week. So this week will be the content of week 6. So I mostly discuss about the theory classes, not the lab classes, because it is not very useful to talk about that. And the lab videos are self-explanatory. You can watch and uh, you can just get the idea like what was going on there. And if you have any questions related to those lecture videos and lab videos, you can ask in the discussion forum. And if you have any question, the live session I am doing, that those questions you can ask me in the live session itself. If you want to give any feedback, then you can give in the session itself, or you can write in the discussion forum also. I will check the questions, like I check the discussion forum time to time, and I'll be able to get back to you. Okay. So the first topic that was discussed, so we have already discussed about photolithography in earlier weeks as well. But since it was discussed again in this week, and specifically this time considering silicon wafer in mind, and the designs that we were discussing, like how to make interdigitated electrodes, or the process of fabricating a microheater will also be similar. Instead of the interdigitated structure, we will have a different design, but that is also will be of some metal. Okay. The process will be similar, and many times we will use silicon as wafer. So this we will discuss considering specifically keeping silicon wafers in mind. So the processes may be little bit different depending on your design, and depending on the wafer that you are using, the photoresist that you are using, the processes can vary a little bit, but the overall process, like the different steps, will be similar. Some maybe few steps will be optional, but photolithography steps are in general you go for photoresist coating, and you will do exposure, and then you will develop. So these are like three basic steps in photolithography. Okay. So what is photolithography? It is creating small structures on wafers using using photoresist and UV exposures. So photoresist I will write PR because I'll use the short form. Okay. And UV exposure, so the word itself is photolithography, so we use some kind of light for exposure, and the light that we use is UV. So UV, ultraviolet, the wavelength of UV is like, it will be less than 400 nanometer. So visible wavelength is from 400 to 700 nanometer, and UV wavelength will be less than that. Okay. We use different UV light, different source. Depending on the source, the wavelength can be different, but the wavelength is in the UV range. Okay. And we use light to write something, and as I mentioned earlier, that since we are using light to write something, So the minimum dimension that we can write using that light or that wavelength, that depends on the wavelength of the source, wavelength of the UV source. Because I mentioned earlier also, it is like writing a line with a pen, and you cannot like a very thin line if the pen tip is very big. So something like that. It's not exactly like that, but the resolution, the minimum dimension you can go for, that depends on the UV light source that you are using. Now, in this course, we are using photolithography. We're discussing about photolithography because this course is on sensors and actuators, and most of the sensors we are discussing is in the micrometer range. So we are discussing mainly micro sensors, MEMS based sensors. So those are mostly in micro dimensions. And to because you can see the wavelength is less than 400 nanometer, so we can make like this micro dimensions using photolithography very easily. If we want to make some, say, very thin structure, maybe few nanometer, that, and then we cannot use photolithography. But for our purpose, photolithography is the main patterning technique. So this is also I discussed earlier, that how we make a sensor. The fabrication process involve different steps, like you do deposition. So deposition will be uniform deposition, right? So after that you want to make some pattern. For patterning, what processes you use? You use photolithography as well as etching. So photolithography plus etching will give you patterning. Okay, I'll write this down. Photolithography plus etching, this will give you patterning of, because we are mainly considering the patterning of thin film, the films that we deposit using some deposition technique. So this is like patterning of thin film. Now, what are the different steps involved in photolithography? So as I mentioned, the steps can vary a little bit different, can be different for different photoresist. For example, the baking condition can be different for different photoresist. But uh, mainly we use few photoresist with silicon, so which are very good to work with. And for those photoresist, you can see the data sheet, all the informations are written. I showed one data sheet earlier also. The baking conditions are written. So what are the steps involved in photolithography? So first step is wafer cleaning. You always want to start with a clean wafer. Now for silicon, you know that there are different cleaning methods, RCA1, RCA2. You can go for like simple solvent cleaning as well. So what is solvent cleaning? You clean your wafer with acetone, IPA and DI water, basically those solvents. Excuse. Just give me a minute. try to speak less and write more for today's session, okay? So please bear with me. After wafer cleaning, what is the step? So the second step is pre-bake and primer coating. So pre-baking is done to remove any moisture content from the wafer surface. And primer actually bonds the photoresist and the wafer. So the primer that we use for silicon photolithography is HNDS. It improves the bonding. Between the photoresist and wafer. What is the next step? The next step is photoresist coating. The next step is soft bake. So this is the most critical step, the fifth step, that is alignment and exposure. So what is alignment? You align your sample or wafer with your mask. Okay, so this is important, like when there is multiple levels of patterning is required. Say you have this wafer and you already have some patterns like this, and you want to make another pattern like this or something. Okay, in this case you will need alignment. Like you have to see, these are very small dimensions, in micro dimensions. Okay, so you cannot like directly see it, so you have to use some lenses, some microscopic arrangement, so that you can see these features, and you have to align your second mask so that finally you will get this kind of pattern. Okay, if you are doing like a single litho, not multiple, but then also maybe you're sometimes you don't want to make like a very large device, so you will use a small piece of your wafer, but your mask may be like very big. There may be different designs, so Suppose you have made like three designs on the same mask, because you will make this mask like one time and you will use it for multiple purposes, say. So this is sensor 1 design, this is sensor 2 design, and this is sensor 3 design. Now on this piece of wafer you want to have this as one design for sensor design, and then you will go for another wafer for the second design, and for another wafer uh, for the third design. So in that case also you may need alignment, because you want your design to be exactly on top of this. So if you just look by, using only your eye, then your alignment the maybe not proper. So like instead of having your design in the whole wafer, you might end up getting a design only here, say. So that is why alignment is critical. So UV exposure, if you have a UV source, then you can like go for exposure if the alignment is not necessary. But generally the like photolithography machines, this two part is like integrated, so the alignment is also integrated along with the UV source and other exposure element, the hardware that is required, because we often use we can use the lithography process for multi-step lithography, multiple lithos, as well as like we may have like a big mask where many of these designs will present, and at a time we want to uh, do lithography on a small wafer, or like only one design from all the designs in the photo. So this step is critical, okay, so that you align your mask properly with the wafer, and you do the exposure for required amount of time. And before exposure you will make good contact between your wafer and the mask. The reason is that if there is a gap, so light may leak from this side. So if this is your wafer, of course photoresist is coated on top of it, and this is your mask, okay, so this is the dark region. When light will enter, so light may go like this if this contact is not proper, okay. Then what the end result will be, what you will end up getting something like an opening here, which is like bigger than your actual size on a mask, okay. So you have to be careful with the contact as well. After the alignment and exposure, what you do, you go for development. So if it is a positive photoresist, the exposed portion will get developed. That means those portion will be dissolved. Those portion will dissolve in the developer solution. And if it is a negative photoresist, the exposed portion will become hard, and the rest of the portion will dissolve in the developer solution, okay. Now for particular photoresist we have particular developer, okay. So you can check the data sheet of any photoresist like SU8, or what is the developer for that particular photoresist. And the last step is hard bake. Okay, so this is required for the photolithography process that we are discussing here, but it may not be necessary in case of certain photoresist. It depends on the photoresist. Again, you can look you can search for any photoresist that is it, and see what are the steps that is necessary for that particular photoresist. So the example that was discussed in the class was how to make interdigitated electrodes using photolithography. So how you will do, you will start with your wafer and say there is metal deposition. So there are multiple techniques to make like metal structure or interdigitated structure. We are discussing one of this, okay. So you have your substrate and this is your metal. So what you will do, you will coat photoresist on top of it. Using a spin coater. Spin coater will rotate at a certain speed, and because of that speed and the viscosity of the photoresist, you will get a certain thickness of photoresist on top of your substrate. Okay. Then you will use a mask that has interdigitated electrode pattern. Now let's say you are using a positive photoresist. So ultimately you want to pattern this metal layer as an interdigitated electrode. So what should be the mask for your photoresist for this purpose? Okay. So I'm just giving you a representation. So your interdigitated electrode will have like multiple combs. I'm just making few so that you get the idea. Okay, there will be multiple fins. Okay, I'm just making one, two here and two, one this side. Okay, now if you are using a positive photoresist, then this mask here, this portion will be dark. Okay, this is like the top view of the mask. Now what you will do, you will use this mask and you will do photolithography. So this, by this I mean that you will align your mask and you will do exposure and development. So the structure you will get will be like this. So this is your substrate and this is your metal. Okay, so I made the mask opposite. So if it is a positive photoresist, then what you want, your mask will be different. Okay, so this is for negative photoresist, and if you have positive photoresist, the mask will be something like this. Most portion will be black, only the portion where you have this interdigitated electrode, that portion will be okay. No, this was correct. Okay, so let me just think. So if the this portion will be dark, so light will not pass through this, so this portion will be exposed. So most portion will be exposed and that will get developed. Okay, so yeah, this is the correct mask. And finally you will have this photoresist in for this kind of photoresist on top of your metal line. Okay, what you will do, you will go for etching. So the metal which are exposed, that will get etched, because you will be using a particular chemical or particular material that actually etches away the metal part but not photoresist. Okay, so the metal portion which is below the photoresist will be like secure, there will be no etching, and the rest of the portion, rest of the metal will get etched out. Okay, so after that, what you will get the so I'll only make the top view of it. So you will have like this uh, kind of structure. Okay, this there will be photoresist and there will be metal below. Okay, now what you will do, you will etch away you will remove the photoresist layer by using acetone, and you will be like left out with the metal electrodes, metal interdigitated electrodes like this. Okay, so choosing the correct mask is important. If your if this portion of your mask is dark, then you will end up getting a different, like opposite pattern, opposite metal pattern at the end, if you use positive photoresist. So if your photoresist is negative, you should use a opposite mask, opposite of this one, to get the correct pattern. So this is about photolithography. If there is any question, you can ask. I hope there are people in the meeting. Okay. If there is no question, then I'm really sorry for my voice today. I'm kind of sick. Soft bake temperature, it was discussed. I don't remember exactly. I think it was 95 degrees Celsius. Uh, but again, that is particularly for that photoresist, for the photoresist that was being discussed in the course. Okay, if you use a different photoresist, the soft bake temperature and hard bake temperature can be slightly different, but mostly in the range of like 90 to 110. Okay, so this was about photolithography. You can ask if you have any doubt, you can ask later as well. I have also discussed this a few more times in earlier live sessions, so I'm not going into the details of it. I have shared some pictures of I have taken some pictures from Google Images. I have included in the earlier PPTs as well, so you can check those also if you want to understand the process more clearly. Next topic that was discussed, signal conditioning circuit. So I mentioned you earlier that we don't use a sensor like alone. Okay, we try to make a system out of it. Okay, so how we do that? Now the basic block diagram was like, we take the output of a sensor, we feed it to some circuit that makes some decision, and based on that, some actuator, the input to some actuator is given. Okay, but before using the output of a sensor, sometimes we need to do signal conditioning. Okay, so the example that was discussed in the videos, that was the signal conditioning circuit for a temperature sensor LM35. Okay, and the sensitivity of this temperature is 10 millivolt per degree Celsius. So uh, the it is it what is the input to this sensor is the temperature, and output is electrical in nature. So it's a like a electronic or electrical sensor, you can say. The output is in volt. okay, and 10 millivolt per degree Celsius. So it gives us an analog output, okay, not digital. So it the sensitivity, this means for 1 degree of Celsius change, the change in voltage, output voltage of the sensor will be 10 millivolt. Okay. Now, what a signal conditioning circuit will do, so it will match kind of the output of the sensor to the circuit that we are connecting. Okay, we don't, as I mentioned earlier, we don't use the sensor alone, we make a system out of it. There will be other circuit, so it's like the interfacing circuit, and first step is to do the proper conditioning of the output of the signal using a signal conditioning circuit, and then you will interface with the other part of our circuitry, okay, other part of our system. I hope that you have watched the videos where this topic was discussed, so it will be easier for you to understand. Okay. The signal conditioning circuit provides matching. So this matching like can be like, you can say it's like an interfacing circuit between our other systems or the other component of the circuit uh, with the with our sensor. Okay. Now, what was discussed in the class was that, say, this sensor can measure like the range of the sensor. You can look, it's the range is very large. I don't remember the exact value, but we are interested only between 0 to 100 degrees Celsius. Okay, so the sensor will give, if it is like 0 degree, that will give 0 millivolt output or 0 volt, and if it is 100 degrees Celsius, so you can use this sensitivity information, so the output will be 1 volt. Okay. Now this output of this sensor is analog in nature, but many times when we want to use it for decision making, we normally compare it with some standard value, and we normally it is easier to use a digital input for our decision making unit. Okay, so we want to convert this analog output to an analog signal to a digital signal. So what we will do, we will use an ADC, so analog to digital converter. So this you have studied in your basic electronics courses. Say we are using an 8-bit ADC, so it will have 2 to the power 8 states, so that is 256 levels. Okay, so that means it will have 0 to 255 levels. Now if our reference voltage for ADC is 10 volt, then uh, 0 level, 0 state will will be 0 volt, and 256 or 255 state will be 10 volt. Okay, now we are interested in 0 to 100 degrees Celsius, that corresponds to 0 to 1 volt, not 10 volt. So what we want to do, we want to convert 0 to 1 volt range to 0 to 10 volt range, and you already know how to do it. We want to improve the gain. We will use a circuit that will give a gain of 10. Okay, so this is our sensor LM35. We will use a circuit with a gain 10. Okay, and then the output will be given to ADC, analog to digital converter. Now remember, here is one thing, uh, like if there is any noise in our output, in the output of our sensor, that will also increased 10 times. Okay, because we are directly taking the output of a sensor and providing it to the circuit that has a gain 10. Normally we may need you we have sometimes we use like a filter circuit to actually filter out the noise. Okay, that is also one component in signal conditioning circuit, but as of now we are considering that there is no error, there is no noise in the output of our sensor, and we are just directly increasing the gain of our output. Okay, now how we can make the circuit to get a gain of 10 or get any gain like say AV. So we normally denote it using that like this notation AV. How we can do that? We all know we can use an operational amplifier to get a gain of uh, 10 or any value depending on the design. Okay, so using an inverting or non-inverting amplifier. Basically you want to amplify your signal. Okay, amplify the strength of your signal. Now I will briefly discuss about op-amp. I will not go into the details. I hope that you already know, like you remember everything about op-amp, because this we study in any like basic electronics courses, at least like a little bit about it, the basic configuration, inverting and non-inverting and differential amplifier. We study all these things. You may have done some lab experiments also using op-amp. Okay, so the basic circuit diagram for an op-amp is like this. If you remember, this is the non-inverting terminal, this is the inverting terminal, and we will apply supply. So this is plus VCC, this is minus VCC, this is non-inverting terminal, this one, this is inverting, this one, and this is our output. The IC for op-amp is IC 741. So you have used this in your lab classes. If this is your IC and this is pin 1, so it's 8 pin IC. 1, 2, 3, 4. 5, 6, 7, 8. So first is offset null. So we normally we don't connect it, but if there is an option between inverting and non-inverting terminal, so ideally for op-amp the voltage at the inverting and non-inverting terminal should be same, like at this point. If not, then we adjust it using this offset null point. Okay, we connect a potentiometer, but let's not consider this. We are considering the ideal condition. We'll consider that the voltage drop at this point and at this point are same. This is the inverting terminal, pin number 2, and this is the non-inverting terminal, pin number 3. And this is minus VCC 4 and plus VCC is 7. So this is plus VCC, and this is output, pin number 6 is output. So just for this session, just remember that pin number 2 is inverting terminal, pin number 3 is non-inverting terminal, and pin number 6 is output. Okay, so this is the pin diagram of IC741 op-amp. Okay, now we can use this IC to get a gain either in inverting configuration or in non-inverting configuration. So let's see first the inverting amplifier. This is just to brush up your knowledge. You have already studied these things. So the circuit diagram will be like this. This is negative, positive, and this terminal will be ground, and we will connect our input here, V in. This is the first resistor and this is the second resistor, and this is our output. So this is the R2 and this is R1, and a current I is flowing here, I. Okay, this is V out. Now we know that op-amp has very high input impedance, so no current flows through this between these terminals, inverting and non-inverting. So actually these the potential at these 2 points are same. Okay, I hope you can hear my voice compared to the background noise. The potential at this point and this point is same. Because op-amp draws no current, that is the ideal condition. So this is grounded, non-inverting terminal is grounded, so this is also virtually ground, we say this. Okay, so the potential at this point is 0. So we can write like a basic case, we can use basic KCL and KVL to solve this problem. What is the relation between input and output? So this is virtually ground. So here we can use KVL. We can write that current I is equal to V in by R1. Similarly, we can write KCL here. Minus I, because the direction is opposite, is equal to V out by R2. Okay, these equations are clear, I hope. And then so the relation between V in and V out will be, you can use this too. So V in by R1 is equal to minus V out by R2. Okay, so V out is equal to minus R2 by R1 V in. Here I am denoting this resistor as R2. It can be written as RF, the feedback resistor. Don't get confused. The relation between output and input in case of inverting amplifier is minus R2 by R1 into V in. Okay, so whatever we input we apply, we get a gain of R2 by R1, and it is inverted. That's why this negative sign. So this is about inverting amplifier. So if we want a gain of 10, we will make R2 as 10 times of R1, and we will invert. After that we will get an inverted signal, and we will again use another inverting amplifier with a gain of 1. Overall we will get a gain of plus 10 instead of minus 10. Okay, that's how we can solve this problem. Next configuration is non-inverting amplifier. I'll use a different color. So the circuit diagram will be like this. This is the non-inverting terminal, and we will apply our V in here. This is our R1. This is our output voltage, and this is R2. So current I flows through it, and the same current flows through it also, this here also. So this current I is flowing like this. And again we will use the concept of this that the potential at the inverting terminal and non-inverting terminal is same. So this 2 point will have same potential, that is V in. We are considering ideal open condition. Okay, so at this point also voltage is V in. So again we will use we will write the current equation. So current I is flowing through here. So I is equal to V in by R1. Okay, so this point is also V in. So this current is I here, so V in by R1, and current I is equal to, so we'll use KVL in this loop. So the voltage is V out. This is divided by R1 plus R2. There is these two resistor. Okay, if we write KVL in this loop, we'll use this two equation here, and our relation between V out and V in is 1 plus R2 by R1 into V in. Okay, now you can see here that we started with an input voltage of some volt, and our final output voltage is multiplied by this term. So this is our gain. We use this AV that denotes gain. Okay, for this case our gain is minus R2 by R1. Okay, so we will design our circuit accordingly to get a gain. Okay, now I have not discussed details about operational amplifier. You have already studied this. This is just to give you an overview and brush up your knowledge, so that when I will go to the questions, then you can just use this equation and solve the problems. Next, so the circuit was discussed how we can make this interfacing circuit for LM35 in the class, and the experiment was shown also. I think many of you have done this experiment in your undergraduate or graduate programs as well. Now next topic was console simulation of a micro heater. So again I will not go into the details of it. The video is self-explanatory. How we can use the software to simulate a design, what are the different physics we use, those were discussed. You can go through the videos, and you can, if you have the access of console multiphysics from your institute, then you can try doing the simulation by yourself as well. Next lab class was on clean room facilities. Again The clean room protocols were discussed, so how you should wear your hairnet, how you should wear your gown, and all the protections that you need to take, and about the air shower, so that if there is some particles on you, then the air shower will like shower it down. And if you carry some pen, diary, or something like that, or your sample box, those things, so what you will do, you will pass it through like a two one way door kind of system, where those your like those things will also get like pass through a filter, so that there is no contamination inside the clean room. So those things were discussed. Also, the lithography room was shown there. You have noticed that there was yellow light in the litho room, that is to prevent some unwanted exposure of the photoresist. So as we discussed, the photoresist are sensitive to UV light. Okay. But photoresist is also sensitive to certain like few wavelengths of blue light as well. So we know that in white light it contains everything from blue to red, right? 400 nanometer to 700 nanometer. So even if you use white light, the properties of your photoresist will change. So that is why for safety yellow light is used in litho room. Okay, these were the things those were discussed in these two videos. I request you to watch the videos and like clear your doubts. The videos will explain everything. So because these are like lab videos, so you will get the picture if you watch the video. Okay. I'll wait for a couple of minutes. If you have any question, then you can ask. Okay, non-inverting term. Yes. So these are the question. You can take a look and try to understand the equation. Okay. So these are like simple circuit. Some basics you should like consider before solving it. The assumptions that I made, that this is an ideal op amp, the input impedance is very high, it draws no current, and the potential at the inverting terminal and the non-inverting terminal is same. All right. I hope that you are actually getting what I am saying. I didn't want to postpone the class, but it's been difficult for me to actually speak today. So if there is no question, let's go to the questions. Okay, so these live sessions are mainly for questions and answers, so but I give an overview at the beginning. Okay, sometimes it takes more time than a question and answer, but I try to include as many questions that I can. So the first question is, I will write down the question. This is not like not only true for console simulation. You can use like a different uh, s- software also. So what is a prototype stage? So it is like you will make a single sensor or few sensor just to check the characteristics. Okay, like how the sensor will behave before going for large scale fabrication. So the options are only one and two statement is true. B is only 1 and 4 are true. Option C is only 1, 2 and 3 are true. Option D is all are true. Okay. So what is the correct answer? Why are simulations performed using COMSOL or any other software before sensor fabrication? Why we do that? Choose the option that suit the best. So first statement is allows exploration of different design, can be of different materials as well, saves on product development cost and time. The actual sensor performance is close to estimated and or simulated, and a sensor design can be directly realized for large scale production without requiring a prototype. So there are only few people in the meeting, so I want answer from all of you. You can write in the chat box. Option D and option C. What about others? I can see that there are four people in the meet. Option D. Okay. So all of you guys have are confused between C and D, right? So let's see one by one. So first option allows exploration of different design. That is correct. We can play around with our design and play around with our material, whichever is like less difficult, whichever is less complex and less costly, I would say, because if you use different material, the cost can be different. Like if you, especially when you go for large scale fabrication, the cost can vary significantly. So we can explore the simplest design. We can find the simplest design that works best. We can find the lowest cost material if we use a simulation software instead of directly going for fabrication. It saves on product development cost and time. Otherwise, if you don't use this software for simulation, what you have to do, you have to, like, you will fabricate the circuit. If you fabricate the sensor, you will test your sensor, and if it works correctly, then it's okay. If not, then you will change your design, change your material, change your process to get the desired result. So that is time consuming, and it involves like a lot of cost because you will consume resources. The third option is the actual sensor performance. So these are true, right? And the actual sensor performance is close to estimated or simulated. We try to simulate, uh, we try to simulate the our design, so in a way that it gives us a very close result, like which we will actually get. So that is why in console, like selecting the particular boundary condition, how, say for example in case of designing a heater, so it is very important that you choose the correct boundary condition and how the heat will flow, because uh, there will be air, if when you use the sensor, it will not be in vacuum, so there will be certain heat loss because of air, because heat will travel from your structure to air, something like that. So you have to consider all those practical scenario while doing the simulation. If you do it correctly, then it will give a result that is very close to the actual result. So this is also true. uh, and the last option is the sensor design can be directly realized for large scale production without requiring prototype stage. So that is what the option D is, like if we consider all of the above. This statement, even though looks true, but it is not true. Like uh, the sensor design, like you will consider many things, you will consider all the practical scenario during your simulation, but certain things you cannot realize, you cannot do it in simulation. Okay, that is why it is not a good idea to go for large scale production before actually making few samples, like few sensors, and checking the characteristics. uh, Say your material property can be a little bit different, right? Say you are using a thin film of some material, and you are using the inbuilt material properties, those are in console, whatever. So you are using uh, a material that is for like heat flow control, and you are using the thermal conductivity of the material, which is like a standard thermal conductive value that was given like already there in COMSOL. But maybe when you are depositing the material, when you are synthesizing the material using some chemical technique, the properties may not be exactly same. You are not using those properties in your simulation unless you make your so what is the ideal way is to that you start with your simulation. You will make your like a sensor first, or the device, and then if the result matches, then you know that yes, everything is correct. If it does not match, then you will see, okay, so the property that I have used, like the, say for example, thermal conductivity, I have used this value, but actually my material has a different value. You will go for characterization. Then again, say you have used the conductivity of your material of certain value, but your actual conductivity is different, so you will see those things. And say you are making some suspended structure, you cannot exactly simulate what will be the air gap between your suspended structure, right? Say you simulated with a certain value, say that the suspended structure and the beam and the layer below it, that will have a distance of say few micrometer. But in practically maybe it is a different value. So you will try to incorporate all those changes, the changes that you actually did during fabrication, due to fabrication error, due to your uh, whatever your like limitations of your process. You will check those and you will include that in your design. Then you will go for the simulation again, and then you will see whether your response and the actual sensor output is matching or not. Okay, and if that is your desired result, then well and good. If not, then you will try to improve your fabrication process so that you actually get the simulated result, because that is what you initially started with and that is what you want. Okay, so this statement is not correct. Where is the cursor? Okay, so our answer is C. 1, 2 and 3 for second and third statements are correct. Okay, let's go to the next question. Without HMDS treatment, oh, photoresist adhesion can be poor due to moisture on the wafer surface. Whether this statement is true or false. It's a very simple question you can answer. I will wait for a minute or so that you can write the answer in the chat box. So this question, this is we are discussing considering like silicon wafer in mind. So we are using silicon wafer uh, for this photolithography process, and we are discussing this considering that in mind. This is true. Yes. So why it is true? You know that like silicon, if we think like pure silicon is in general hydrophobic. It does not attract moisture. But you know that when we keep silicon outside, there will be like a very thin silicon dioxide layer on top of it. Even if you try to dip it in HF solution, hydrofluoric acid, to remove SiO2, and you take it out, and after some time there will be an SiO2 layer. It will be a few nanometer. You are not doing like growth of SiO2 uh, like at a high temperature, but there will be few nanometer. So that is the native oxide. Okay, and SiO2 is hydrophilic in nature, so it attracts moisture. If you are working like in a lab that where the humidity level is very high, then it will, the bonding between the photoresist and your wafer will not be good. So uh, we that is why we go for this primer coating or HMDS coating, so that the adhesion between the photoresist and our wafer is good. If you have like if you start with a very hydrophobic surface, then you don't need it. If the adhesion between the wafer and the photoresist is good, but since we are discussing silicon, and silicon even though is hydrophobic, but there will be an SiO2 layer on top of it, that is the native oxide, so we often go for HMDs. And one more thing I want to say, that these are from my personal like experience. So what we do in our labs when we do lithography, and when we operate any machine, we try to control the humidity level as well. So in the class that we are discussing, that different clean room protocols, and you've already like we already aware of different kind of filters so that there is no contamination. One is also one thing also important, that you maintain the proper temperature and humidity while we are doing some processes, because that will also affect your end result significantly. So what we do in our lab, we try to maintain the humidity like level low. That is always good for the machines. We don't want like moisture or humidity to damage our system. So try to keep it below 75. That is in our lab, so it may be different somewhere else. So these are the things you should remember while going for fabrication. If you are working in fabrication of sensors, then you should remember these things, that sometimes you know you are doing everything right, but you are not getting the desired result. Maybe that is because of the environmental effects. That is why what I used to face like a lot during my MTech project, because I used to synthesize this chemical, but it never I failed many times just because the temperature was very high at the time, and I was not able to control the temperature properly. The reaction that happens at a particular temperature, but I was not able to control it properly because of the temperature fluctuations. Temperature and humidity, that affects a lot. So the answer is true. Okay. I will write a note here. The hydrophilic nature of SiO2 allows moisture absorption, which leads to pore adhesion of photoresist. HMDS prevents this by making this surface hydrophobic. Hydrophobic means it repels sweat. Right, next go to the next question. So I've discussed about LM35 temperature sensor. The question is, I hope that you remember it. You can, like, I can't see you, you can just Google and tell me the answer also, but I hope that you actually remember it. What is the sensitivity of LM35 sensor? Option A is 1 millivolt per degree Celsius. B is 10 millivolt per degree Celsius. C is 100 millivolt per degree Celsius. Option D is 1 volt per degree Celsius. So, what is the answer? B. Yeah. So, I hope that you actually remember the answer. Okay. So, the answer is B, 10 millivolt per degree Celsius. Now, here, like one thing I want to mention that so what we want normally, we want the sensitivity of our sensor is very high. So, or we can say that the resolution is very good. So here you can see, say if our sensitivity is very high, say per degree Celsius, if it gives us a very like large voltage, then what can be the advantage if I think about the system or the circuit associated with it. Say we are not using our any interfacing circuit, we are directly measuring the voltage. So if the voltage is high, say it is 100 millivolt or 1 volt, so if you are measuring with a device with a multimeter, say, that can measure it cannot measure very accurately, like it cannot measure very small voltage accurately. Okay. And it cannot differentiate like a small voltage like 100 and 110, maybe it will not be able to give like differentiate properly. Then if your sensitivity is good, if a 1 degree change the change is 100 millivolt, then you will be able to measure it. Okay. If the change is very small, then you may not be able to measure it, so you have to use a different circuitry, again some interfacing circuit to make it work. Okay. This way, if it is give like a good sensitivity, then it's a good sensor, we say. But then there are other sensor characteristics as well, like if it the repeatability is not good, if the precision is not good, then we cannot say that the sensor is good or useful for our application. So if it is 25 degrees Celsius, what will be the output if the sensitivity is 10 millivolt per degree Celsius? So multiply with 10 millivolt, so it is 250 millivolt or 0.2 volt. So you should need a system that can actually measure this volt as 0.2 volt. So it is not difficult to measure 0.2 volt, but if it's a very low temperature, then maybe you will not be able to measure. Okay, let's go to the next question. So this question is on op-amp. In the assignment questions, no numerical question was given, I have checked, but I have included a few numerical questions on op-amp, like simple gain calculation or output voltage calculation, because these are very easy and I think you should know this. You already know this, so just do the calculations. It will be like a you have already done this, so this is just practice. So the question is, an inverting amplifier is designed, so I have given the circuit also for your reference, not circuit. An inverting amplifier is designed using op-amp with feedback resistor of 100 ohm, 100 kilo ohm, and an input resistor of 10 kilo ohm. If the input voltage is 0.5 volt, what is the output voltage? Very easy calculation you can do and tell me the answer. So remember, this is inverting amplifier. So the gain is minus R2 by R1. So R2 is the feedback resistor and R1 is the input resistor. Okay, for inverting amplifier. So the input voltage is given. What is the output voltage? Minus 5 volt is minus 5 volt is the correct answer because it is an inverting amplifier. So the sign is also important. See why the sign is important. So say um, like we are discussing this in the sensors and actuators course, and you have noticed that we use like Arduino board with our sensor to make an actuator work, like to make a motor run or make a switch turn on and off, all those things. So plus 5 volt and minus 5 volt will be very different. Say your threshold level is like 2 volt. If it is above 2 volt, you will consider it will turn the switch on or off. So if you directly use your inverting amplifier and that will give like an inverted output, then the switch or the motor or everything that will be always off, like because it will be a negative value that will be less than 2 volt or whatever the threshold voltage you are considering. So that is why you should be careful whether what is the configuration and what is the circuit that you are using after that. So right here. The solution is the gain. So this is the voltage gain of our amplifier, AV. So that is why we denote as V. So this is the voltage gain is equal to minus R2 by R1. So this will be ground, and this is our V in, which is equal to 0.5 volt, and this is 10 kilo ohm. This is 100 kilo ohm. Now I hope that you know why we connect this feedback resistor in the inverting terminal, not in the non-inverting terminal. Okay, what is the reason? If you don't remember right now, you can recall like what will be the gain if we just connect it in the inverting terminal. We always connect the feedback resistor in the non-inverting inverting terminal, not in the non-inverting terminal, unless we want to use it for certain other application. What is the application? You can't recall. So this is 100 kilo ohm, and the gain will be minus 100 by 10, so this is minus 10. So V out will be AV into V in, so it is minus 10 into 0.5 volt, which is equal to minus 5 volt. Okay. Let's go to the next question. Similar question, but it is for a non-inverting terminal. This is just for your practice. Again, I'm telling you, just to remember, just that you can recall your formulas, recall the formulas that you studied probably like initial stage of your engineering, really, or your undergraduate program. So the question is, a non-inverting amplifier has feedback resistor of 47 kilo ohm and input resistor of R1. Okay, input, don't get confused here. 4.7 kilo ohm. If V in input voltage is 1.2 volt, what is the output voltage? So your V in is here, which is equal to 1.2 volts. So these are like DC signal, can be analog signal as well. And this is 4.7 kilo ohm. This is 47 kilo. So what is V out? If you want, the gain formula for non-inverting amplifier is 1 plus R2 by R1 or RF by R1. Feedback resistor is often denoted as RF. $13.2, yes. Gain AV is equal to 1 plus 47 by 4.7, so 1 plus 10 is 11. V out is equal to 11 into 1.2. Okay, so this is 13.2 watt. Yeah, non-inverting amplifier gives you like a same uh, sign of V in and V out, but you can see that this because of this one plus thing we get gain like 11. The gain we got here 11. So sometimes it is difficult to do this, not difficult to do the calculation, but to find the right resistor value to get a gain, particular gain. So in invert the that is easier for inverting amplifier. So you can see that to get the gain it is easier to find a resistor which is like of 10 times using inverting amplifier, but we have to use like two open. So to again to invert the signal, let's go to the next question. So this I have just added. If you have watched a video of console simulation of micro heater, then you will be able to answer. So what are the physics those are used for micro heater simulation? This is in console multiphysics, so the question is incomplete. Micro heater is a very basic component like for many sensor design, because many times like the sensing material actually works at a higher temperature, not at room temperature. So we need to design a micro heater along with our sensor. So this is one problem also, like one area uh, where we can work. So we can try to make the sensor work at room temperature. So people work on that, low temperature sensing or room temperature sensing. Because see, if you are using a heater, if you are doing the measurement at high temperature, then what it means that you are constantly using power for measurement. You are constantly using power to make the sensor work. That is what we don't want in many cases. If your sensor should remain on most of the time, then the power consumption will be a lot. Again, if you are using a lot of sensor, then also your power consumption will be a lot, especially in case of IoTs or other application. Because how you heat your heater, micro heater, you will apply some voltage, and because of Joule heating, the temperature will rise, right? So you are applying voltage, that means you are applying power. Okay, so there is non-zero power consumption, so it is not working. So that is what people try to make a low temperature sensing that will essentially give us low power consumption of the sensor. So what are the physics used for micro heater simulation in console, if you remember? No? Okay, if you don't remember what are the physics those were used in micro heater simulation, you can just tell me the different physics so that you know those are available in console. You can just name a few also. Or if you have used console and planning to use console, what are the physics that you are going to use? You can tell me that as well. Okay, it's fine. I did not watch, but if I remember correctly, then you told me that you are planning to use console. So, any idea like, do you have any plan like I will use these physics and I want to use it for this purpose, so I will maybe need this physics. So it's okay if you are not clear with like your plan and you have not started with console. I'm just I just want to know that, like, what physics you are using or you are planning to use. I have also not done micro heater simulation in console by myself. I have seen people in my lab, they use it for simulation, like what is the maximum temperature the structure can give. Okay, all these things I have seen that some of my lab mates do, but I personally have never done. Okay, yeah, fine. So I will write down the physics tools by used. You can watch the video again, and if you have the access, I would suggest you that you do some simulation as well. Solid mechanics, because we are like simulating a structure. Okay, we are simulating a structure that will expand due to the because of thermal expansion. That is why we are using the solid mechanics physics. Then we also use heat transfer in solids, and electric current, because we are relying on joule heating, so we have to apply some voltage, some current. Because of that, uh, the material will heat up due to joule heating. Now the multi-physics use, so these are like interdisciplinary thing, you can say. Thermal expansion, temperature coupling, electromagnetic heating. Okay. Let's go to the next question then. Clean room maintain a positive pressure to prevent contamination from external environment. Whether the statement is true or false. Can tell me the answer in the chat box, and also the reason why you think that it is true or it is false. It is true. And why it is true? See, it is not always easy to maintain a clean room, so you have to make sure that the filters are working properly, everyone is following the clean room protocols properly, the machines are well taken care of. And one thing also, we should keep in mind, like while maintaining, is that the clean room should have a positive pressure to prevent contamination from external environment. The reason is that in that way, so the air flow will be from inside of the clean room to outside, not from the outside to inside. If air flows from outside environment, then again the main purpose of clean room will not be solved. We want a particle free environment for our work, like working and testing, like for fabrication and characterization of our devices or sensors, or in whatever area you are working in. So you know that air will flow from high pressure region to the low pressure region, so air will flow from clean room to outside. So every time when someone opens the door, that uh, like uh, a positive pressure will ensure that there is no contamination. Preventing dust particles or any other particles from entering when the doors open. Okay, so this is the next question, and if I don't have time, then I will not go for the next, like on any more question. You can uh, tell me the answer for this question in the chat box. So this question is match the following. So you should match A B C D with 1 2 3 4. Uh, what indicates, like what resonates more with A, UV light, whether so I can tell you the one answer that it causes photoresist exposure, like so A matches with 2, so that's how you can tell me the what matches with B and C and D. Uh, rest those are in the table. Okay, you can tell me the answer. So minimize load on HEPA filter. So this is for the last question. Yes. So yes, the particles HEPA filters will filter the particles, but again, like the maintenance cost will be high if we leave everything to the HEPA filters, right? So we try to minimize the load as much as possible. It's true. Okay, so I should probably stay in this slide so that you can answer. B A with 2, B with 4. Okay, so let me help you. Yeah, correct. So the answer is UV light, as I mentioned, that will go with it causes photoresist exposure. So UV light changes the properties of photoresist. Either it can harden the photoresist if it is a negative photoresist. So UV exposure will lead to cross-linking of polymer. Uh, those are present in photoresist, and that essentially will make the photoresist hard if it is a negative photoresist, or it will make it soft the if it isn't sorry uh, cross linking will happen if it is a negative photoresist, and due to exposure the photoresist will become soft, uh, and it will dissolve in developer solution if it is a positive photoresist. So A with 2. B, yellow light. Why yellow light is used in lithorum? That is to prevent unwanted exposure. So remember that we are discussing like UV light changes the photoresist properties, but in like blue light also, I mean the lower wavelength in white light. So the visible range is 400 to 700 nanometer. Lower wavelength range also affect the properties of photoresist. So that is why we don't use white light in a litho room. We want to we don't want any unwanted exposure due to our white light sources. So that is why uh, we use yellow light in a litho room. So you know that we nowadays we have this habit of using phone like all the time. uh, it is not a good idea to use there, because in our phone the light will be like a white light, and if we use torch that will be also like that will expose the photoresist, right? We don't want to use that. We use only yellow light in litho room. And why I said this, because we have this habit of using phone all the time, because I do litho in my lab, and sometimes like uh, we also forget that we have to maintain like proper decorum in the lab, so that we don't do like expose our photoresist unwantedly. So we turn off any white light source when we do litho in the litho room. C is photoresist. So photoresist is a light sensitive polymer. So C with 1. And D, photomask. So okay, it defines the patterns to be transferred. Okay, so it's with 3. So photomask, it has like transparent and dark region. Usually it is a chromium coated on glass substrate or quartz substrate, so that will be transparent, and chromium will be opaque, so light will not pass through it. Okay, so uh, again to make the photo mask, people use again lithography, right? We will do the chromium deposition So that is, so we give it to like some manufacturing, mask manufacturing people. They will make it for us. But again, the process is same, like process is like that. We do make patterns of chromium on top of your on top of our mask, on top of the substrate, and that substrate will be transparent so that light will pass through those transparent region where we want exposure. Okay, that's it. So what is photomask? It is a chromium coated glass substrate basically, right? So don't have much time. So if you have any question, then you can ask. Otherwise, I will stop the session here. There is no question. Okay. Thank you. If there is no question, then thank you for attending the session. I will end the session here. Uh, I hope that the session was useful. See you on next Tuesday and then the next live session. Okay. Thank you, everyone.
Thank you, ma'am.